All right, we'll go ahead and get started. Just to introduce myself, my name is Amanda Reinhart, and I'm a marine forecaster with the National Hurricane Center Tropical Analysis and Forecast Branch. And just a few housekeeping items before we get started. We are recording this webinar, and we'll be recording tomorrow's webinar too. And once those are completed, we'll send them out to all of you as long as you've signed up with your email. If you're having technical difficulties, try logging off and logging back in. That usually does the trick. And if not, I'll be happy to help you with whatever difficulty you may be having. And for today's webinar, we'll be talking about the National Hurricane Center's Hurricane Specialist Unit and their products. And our speaker for today is Dr. Michael Brennan, who is normally the branch chief of HSU, but is now the acting deputy director of the National Hurricane Center. And Mike, whenever you're ready, take it away.
Great, thanks Amanda. Thanks everybody for coming this afternoon and for taking part in our webinar. What I'm going to go over today is an overview of NHC's hurricane forecast operations and products, talk a little bit about the products that you use or hopefully you're using, a little bit about our forecast verification, some of the new things we're working on, and hopefully to have some time for some questions here at the end. So I'm going to move my webcam out of the way and we'll go ahead and get started. So what I want to first talk about is, NHC from our position here, we're really providing the big picture look at the tropical cyclone. We're following the system throughout its entire life cycle. We're making the forecast of, where is the storm center going? How strong is the storm? How big is it? What are the large scale impacts? Looking at wind, storm surge, rainfall, and obviously the marine impacts that get then translated out through the marine forecast that come out of TAFB and the Ocean Prediction Center and elsewhere. But again, we're following the storm its entire lifespan. Now, really local level impacts are provided by the National Weather Service weather forecast offices in the US for their respective county warning areas, and by the various meteorological services in other countries within our area of responsibility. They're taking sort of our large scale forecast for the storm and then sort of focusing it down and narrowing it down to those local level impacts at the community scale. So just an overview of our forecast cycle. So we operate basically on a 6-hourly cycle when we have a cyclone, and it starts off at the synoptic hours 0, 6, 12, and 18 UTC. That's when we basically start the analysis process that culminates in the forecast process that culminates in the issuance of the forecast advisory package 3 hours later. So at that initial time, that's actually when we issue the tropical weather outlook that comes out every 6 hours. Talk a little bit more about that in a minute. If we have a tropical cyclone with watches and warnings in effect for land areas, we'll issue an intermediate public advisory at that particular time as well. And as I mentioned, that's when our sort of forecast cycle begins. We get our satellite intensity and position estimates, any aircraft data. The hurricane specialist is doing their analysis sort of in that first 45 to 60 minutes of the forecast cycle, and we'll talk a little bit more about that process in a minute. Then we basically initialize and retrieve all the model guidance, and in that next hour, we basically make the forecast. So we basically have about an hour where we put the entire forecast together, and then we have a coordination call, and we basically talk to our weather service partners, DoD partners, and the Navy especially, and give them a sort of an update on what we're changing in the forecast. The forecast is ready for at least preliminarily for them to take a look at. We do all our other coordination about watches and warnings and hazard statements. And then that last hour of the forecast cycle from 2 to 3 hours in is basically putting the advisory products together, adjusting for any last minute data or observations or changes that have to be made, and then actually getting the forecast out. And then basically the next 3 hours is looking at other data, model data that comes in, and then if there are any more frequent updates that are required or special advisories, those would happen during that period of time. And then the whole process starts over again at the next 6-hourly synoptic time. So as I mentioned, we start off with analysis. So the hurricane specialist is really looking at all the available data we have, and we're basically trying to figure out first, where is the storm? That would seem like a rather obvious thing to be able to find most of the time. You think about when you have a hurricane with a well-defined eye, it's not too hard to figure out where it is. But for weaker systems that don't have an apparent, easily identifiable center in satellite imagery, especially at night, you could spend 30 or 45 minutes just trying to figure out where the system is right now. And that can be a non-trivial part of the forecast process, because depending on where the center is might affect your estimate of how strong the storm is, what the initial motion is, what the steering flow is. And more importantly, all of the forecast track guidance that we look at, that we'll talk about in a little while, is going to be anchored on where you think the storm is now. So if your estimate of where the storm is now is off by 40 nautical miles, then your entire track forecast is going to basically start with a 40 nautical mile error and probably get larger from there. So, the amount of data that we have to locate a storm or do any of this analysis varies pretty widely. For storms out well away from land, we're almost entirely reliant on remotely sensed data, largely from satellites. In the western half of the Atlantic basin, we have the luxury of having aircraft reconnaissance that we can send into storms that can give us direct measurements of where the storm is, how strong it is, how big it is. We also can do that for some storms, especially hurricanes threatening the Pacific coast of Mexico. And we have ship and buoy observations, primarily in closer into land areas, and surface data from land observation stations as well, sometimes radar data. But the amount of data we have to work with can vary quite dramatically from one forecast cycle to the next, or even from one storm to the next. Then the hurricane specialist is trying to figure out how strong is the storm. What are the maximum sustained winds? So sort of the peak 1 minute, 10-meter wind that in the storm circulation that's sort of representative of the larger scale storm at the time. Sometimes, again, we have lots of direct measurements of this from aircraft data, radar, buoys, ships, surface observations. Other times, the intensity estimates are based solely on the Dvorak technique, which is essentially a pattern analysis technique that looks at visible and infrared satellite imagery and gives you an estimate of how strong a storm is. So there can be some significant error bars there. Then how big is the storm? How far out do the 34, 50, and 64 knot winds go from the storm center? And we do this in a quadrant by quadrant analysis. For this data, again, we're pretty reliant on ships and buoys, aircraft data when we have it. If we don't have those, we hopefully will get some scatterometer passes from satellites like ASCAT that provide swaths of ocean surface vector wind data from polar orbiting, from polar orbit. But again, those data can be pretty sporadic, and there are times in an open ocean storm where you really have very little data in terms of analyzing the structure. So again, the error bars for those can be quite large as well. And again, if you're off in your analysis of any of these parameters, it's going to affect the quality of the forecast. So we talked about analysis uncertainty. So just for, when we're talking about location of the center, so when we have tropical storms, our best estimate of the accuracy or uncertainty in the analysis of the center position ranges from about 25 to 45 nautical miles. It's probably on the higher end for those weaker systems, especially at night when you don't have the benefit of visible imagery, which gives you a better look at the low-level cloud structure. For hurricanes, the analysis uncertainty starts to go down a little bit, especially when you have stronger hurricanes. They start to see an eye feature that really can help narrow down the uncertainty. And then for major hurricanes that typically have a very apparent eye, well-defined eye and satellite imagery, the uncertainty drops down to the 5 to 20 nautical mile range. Our analysis precision that we provide is basically to the 10th of a degree latitude longitude. So that's kind of getting down to that sort of 5 to 6 nautical mile range. We can't really get more precise than that. In terms of intensity, when we have aircraft reconnaissance data, we think our intensity estimates are good to within about 10%. So if we say a hurricane has a maximum sustained winds of 100 knots, we're basically saying, it could be anywhere from 90 to 110. The uncertainty can be larger if you're only relying on satellite intensity estimates, especially the higher end of the Dvorak scale. A half a T number could be 15, 20 knots difference in the intensity analysis. And so you can have some really widespread. This is a plot from Hurricane Iota, where there's some significant uncertainty and disagreement between some of the aircraft data and what we're seeing in satellite, what we're seeing at flight level, and what we're seeing at the surface from the aircraft data. So more data doesn't necessarily make the picture any more clear, but certainly for sort of more well-behaved typical structured systems, aircraft reconnaissance data really helps to narrow down the intensity uncertainty. We talked about the wind radii. We think the tropical storm force wind radii are good to within about 25%. So if we say the tropical storm force winds go out 100 nautical miles from the center, it could be anywhere from 75 to 125 nautical miles. And again, in that particular quadrant, The hurricane force wind radii are a lot more uncertain. Really, the only direct measurements we have of those typically come from aircraft reconnaissance data. And even with that, there can be significant uncertainty because the aircraft's only sampling about 2 to 3% of the entire wind field of the storm. So we're even then, we're only providing a pretty crude estimate of what the wind field looks like. And we think those hurricane force wind radii are good to within about maybe 40% or so. Here's just another example of a visual way you can talk about the wind size uncertainty. Again, we provide the wind radii, both analysis and forecast, in 4 quadrants of the storm, and they represent the maximum extent of those winds in that particular quadrant away from the center. So that doesn't mean that, say, in this particular example in the northeast quadrant, there are tropical storm force winds everywhere within 160 nautical miles in the northeast quadrant of the center, but that somewhere in that quadrant they extend out that far. Now, when we have a storm near land, we have to account for the extent of the winds over the open water portion of the quadrant, so you can get some really distorted wind radii until the entire quadrant moves definitively over land, and that wind field will start to collapse. But again, the radii represent the largest distance from the center in that particular quadrant. And that's about the best we can do in terms of analysis and forecast. We're not able to really provide a full 2-dimensional analysis of the surface wind field. Okay, let's talk about forecasting. So, the first two parts we'll talk about here are track and intensity forecasting. So track forecasting relative to intensity and structure forecasting is a relatively simple problem. Most tropical cyclones are generally steered around like a cork in the stream. They are something that's embedded in the larger scale flow in the atmosphere that's governed by these large features, these ridges and troughs that you see in this upper image in the upper right. And you see the jet stream, and you see these other very large scale meteorological features that are moving the hurricane around. And because these features are large and they're relatively easy to measure with radiosondes and satellite data, and there's more and more of that data going into numerical modeling, the numerical weather prediction models, particularly the global models, have gotten very, very good at forecasting tropical cyclone track, because again, we're dealing with these sort of large scale features. Track forecasting gets more complicated in some situations, especially when the large scale steering flow is weak and storms tend to stall or they'll tend to drift around. In those kinds of cases, the motion can be determined more by sort of internal processes going on in the storm. And then also when there's structural uncertainties in the storm and we don't know sort of what level of steering flow is going to move the storm around, if the storm's going to be strong and deep or shallow and weak, even if we get the large scale pattern right, it's hard to know exactly how fast or what direction a storm might move in that situation. And those are the two scenarios where we can result in some really large track forecast errors. And then there are times when the large scale pattern itself is very difficult to predict. And those can be situations where 3, 4, or 5 days out, you can rack up some pretty large track forecast errors. But those are typically the exception rather than the rule. On the intensity front, intensity is an inherently more complicated problem because you're dealing with the multi-scale interactions, you're dealing with interactions between the atmosphere and the ocean. You're not only having to figure out what's going on in the large scale environment around the storm, but you're now having to understand what's going on in the scale down to the size of individual thunderstorms, what's going on in the eye wall, in the core of the storm, how the ocean is interacting with the lower atmosphere. And you have to get the track right. You have to get temperature and moisture patterns in the core and in the near storm environment. You have to understand what's going on there. And there are also these internal processes, things like eye wall replacement cycles, that are quite difficult to predict. And we can see them happening. We don't always know how they're going to evolve and what the ultimate intensity of the storm will be when they're done. But those can wreak havoc with sort of intensity forecasting. And then there's also the fact that intensity can change very, very quickly. We see rapid intensification and also rapid weakening in storms that it can be very hard to predict, especially deterministically when you're trying to make a forecast 12 or 24 hours in advance. You may know that strengthening is likely, but you don't know exactly when it's going to start, how long it's going to last, and what the actual peak will be. So you can rack up some pretty big intensity forecast errors in those situations as well. But the good news is that the intensity forecasts are actually getting better now, which is something we haven't been able to say up until just recently. Now we get to forecasting structure. We talked about the uncertainty that's just there in the analysis of the 34, 50, and 64 knot wind radii. Well, there's even and even more uncertainty in forecasting how that structure is going to evolve. There's not a whole lot of guidance available. We use a lot of climatology and persistence information. We know, and we try to account for things like, is the storm strengthening or weakening? Generally, a strengthening storm is going to get larger in most senses. Are the conditions changing? Is the storm coming out of the deep tropics and into the subtropics and mid latitudes where the wind field typically is going to expand, or is the storm undergoing extratropical transition and the wind field is going to become very asymmetric? How much is the wind circulation of the storm interacting with land such that the wind radii are going to feel the effects of friction over land and start to decrease? Is there going to be an asymmetry in the wind field? Do we have a storm that's moving very quickly where you're going to have an enhanced wind field on the right side of the storm circulation and a degraded or much smaller wind field on the left side? So all these basic ideas we're trying to capture, again, as we make those coarse wind radii forecasts. We make 34 and 50 knot wind radii forecast out to 72 hours. We forecast the 64 knot wind radii out to 48 hours. We are doing some in-house experiments this year where we're forecasting the 34 and 50 knot radii out to 5 days, and we're going to see how those turn out this year. So let's talk about track forecasting. So here is our 5-year average track forecast error in the Atlantic Basin from 2017 to 2021, so the most recent 5 years. So you can see that the track forecast errors increase pretty steadily, basically 30 to 40 nautical miles per day out to about day 4, and then they go closer to 50 nautical miles between day 4 and day 5. But in general, we sort of see this nice linear increase of, about 35 nautical miles per day in terms of track forecast error on average. Now, most of the errors are actually smaller than the averages because the average gets skewed by these very large errors. I talked about there are some situations where you make some really large track forecast errors. These are the day 5 errors from that 5-year sample. And you can see that the average track error is about 170 nautical miles. So it's sort of in this bar here. Whoops, sorry about that. And you can see that more of the errors are a lot smaller than that. But we have some errors that are a little bit larger. And then we have a few errors out here where we have day 5 errors that are 400, 500, even 600 nautical miles. Now those large errors tend to skew the average and pull it to a little farther to the right. But most of the time, the errors are actually better than the 5-year at or near or below the 5-year average value. How have error forecast trends? Track forecast errors been trending over the last 50 to 60 years? These are average NHC track forecast errors by decade. We'll start in the 1960s here when we started routinely making 3-day track forecasts. And you can see from the 1960s and 70s and 80s, there were some very small improvements in track forecast error. But again, here at day 3 in the 1980s, the average track forecast error was almost 350 nautical miles. But then as we went into the 90s, we had a huge reduction in track forecast error, and that's continued over the subsequent decades now to the point where our track forecast errors over the last couple of years, 2020 and 2021, are about a quarter of what they were in the 1970s. So in 1970s, the average track forecast error at day 3 was probably 375, 380 nautical miles. Now it's about 70 nautical miles. So we've seen pretty dramatic improvements, and these have largely been driven by advances in numerical weather prediction modeling. We talked about models are run at increasingly higher resolution, increasingly more sophisticated depictions of the processes that happen in the atmosphere. There's a lot more data going into the models. We're using the data that goes into the models in a smarter way to come up with a better analysis of the atmosphere. So these are all paying dividends in reducing the track forecast error. And that's been basically a steady process over the last 30 to 40 years. And here's a way to visualize just how the track forecast error has changed in the last 15 years or so, 15 to 16 years. Here is a forecast for Hurricane Katrina using the cone that what the cone would have looked like in 2005. And remember, the cone is developed so that 2/3 of the time, it's the 67th percentile of our track forecast error. So that 2/3 of the time, the center of the cyclone should remain inside the cone based on the previous 5-year errors. So the cone in 2005 would have been created using track forecast errors from 1999 to 2004. And you can see that the size of the cone, say around 72 hours, which is this last forecast point here, stretches all the way from essentially the Texas-Louisiana border over to about the midpoint of the Florida Panhandle. Now, if you look at the size of the cone in 2021, you can see how much it shrank because the cone error, the track forecast errors that went into the cone from 2021 are basically from 2020 to 2016. If you toggle back and forth, you can see how much that error and the visualization of how much that track forecast error has decreased. The cone now would extend essentially from the central Louisiana coast over to the Florida-Alabama border. Now, one of the main roles that the human forecaster plays in making the track forecast is in exerting some continuity on how much the forecast changes from one cycle to the next. Numerical forecast models don't have any conscience. They're not going to think about, well, if I move my forecast over 300 miles to the east, well, that's just how it solves the equations and forecasts the storm to move in that cycle compared to its previous cycle. But if our forecast moves around that much, then it's not very useful to end users. So if we're flip-flopping or doing this windshield wiper effect and we're jumping all around from one cycle to the next, it really damages the credibility of the official forecast. So we try to make changes to the previous forecast in pretty small increments. We try to nudge the forecast in a given direction. And if there's a big shift in the model guidance, we're going to be slow to bite off on that usually. And we're going to wait and see if that big shift persists over several model cycles before we make a big change. Now, sometimes that means that we're going to be slower than the models are to show a change that actually happens. But in other cases, we don't bite off on a change in the models that turns out to be incorrect. And that was an example of that was Hurricane Laura in the Gulf of Mexico, where the models before landfall were showing a pretty significant shift over to the track to the west toward the Houston area. The NHC forecast didn't really bite off on that and kept the forecast in western Louisiana, and as a result, ended up verifying better than the model guidance did that particular cycle. So another way of looking at this is in this diagram where we're looking at track forecast error on the y-axis and the consistency of the forecast from one cycle to the next on the x-axis. And this is for 96 hours in the Atlantic Basin over the last 3 seasons. And what you're looking at here is the track error and the consistency for the NHC forecast, as well as the forecast from the GFS, the European, and the UK Met, 3 of the better global models for forecasting track. So what you see is the NHC forecast has a lower average error than any of the individual models, but it's also a fair bit more consistent from cycle to cycle. So at 96 hours, the NHC forecast is only changing by about 60 or 65 nautical miles from one forecast to the next. The GFS and the European are moving around by 80 to 85 nautical miles, and the UK Met's moving around by 110 nautical miles. So the NHC forecast is not only better on average than any one individual model, it's also more consistent from cycle to cycle. So we're sort of sorting through those model trends and imposing that consistency, and in the end, giving you a better forecast than you would get from any individual model. So the tools we use to make the track forecast, we talked a little bit about models already, and I'm sure everybody's seen these spaghetti plots, so-called, or these model plots, and they're really ubiquitous out there on the internet and on social media. And it's important when you look at these to think about what these lines actually represent. And are they accurately conveying the uncertainty in the track forecast? Should they all be given equal weight? And what's really not on these plots that you might be missing if you're trying to infer, how the forecast might change or what NHC is trying to look at or do based on what you see in these model plots. So when you have a series of spaghetti plots, we can break down the models and we'll go through an overview of sort of what's in them. One of the things that's plotted on there is something as simple as extrapolation, which we might use for a very short-term forecast, like 6 or 12 hours, especially if the models aren't handling the motion well in the short term, but it really has no utility beyond that time and is not really a skillful forecast aid. We have things like climatology and persistence that used to be used as forecast tools 40 or 50 years ago, but they're really not competitive forecasts now. They're just a baseline that we compare other forecasts against. Sort of where would a storm typically go if it was in this location at this time of year? We have much better tools than those now. We have things like global models. We just talked about the global models, the GFS, the European, the UK Met. These are typically the best forecast models for tropical cyclone track. They handle the large-scale steering pattern and the steering flow really well. They're developed not specifically for hurricanes, but for general weather forecasting. But they do have some weaknesses in that they don't really, still can't really resolve the details of the inner core of a hurricane. And they sometimes struggle with storm structure and intensity, which can negatively affect their track forecast. Then we have the regional hurricane models, things like the HWRF, HMON. These were developed specifically for forecasting tropical cyclones. They're some of our better models for forecasting intensity. And so because they're run at very high resolution, they can start to resolve some of the inner core processes. They may be run with an inner nest that's down to this on the order of a kilometer. So you can start to resolve things like the eye wall and how the hurricane's interacting with its environment. But they still tend to lag the global models in forecasting track because their models are run at such high resolution. They don't cover the whole globe, but they cover sort of a limited area centered around the storm, which can degrade some of the longer range track forecasts at times. Then we have consensus aids, and these are blends of models. These are averages or combinations of models that are typically our best track forecast guidance, especially if the member models all show a similar forecast scenario. By sort of averaging or blending them together in different ways, you can sort of smooth through the noise and come up with a better, more consistent forecast. Now, this consensus approach doesn't work well when the members forecast sort of a bimodal distribution or very different track forecast scenarios, when the answer is probably going to be one or the other and not an average of the two solutions. But that's a relatively rare occurrence. So now let's move on to intensity forecast error. These are the 5-year errors for intensity forecasts in the Atlantic Basin from the Hurricane Center. So what you're looking at again from 2017 to 2021 is the intensity errors gradually increase through the period. By day 1, our average intensity error is about 8 knots. It's about 11 knots at day 2, 12 knots at day 3, 13 knots at day 4, and about 15 knots at day 5. Now, so you can see that those gradually go up, and you can see them start to level off out once you get beyond about 2 to 3 days. But here's that intensity forecast error trend diagram that's similar to what we showed for track. Now, the story for many years has been that track forecasts were getting better, but intensity forecasts were not. But that's really changed. If you look at the average errors from the 70s, 80s, 90s, and the 2000 to 2009 decade, that was pretty much the case. The intensity forecast errors were only showing very small sort of incremental improvements. But from 2000, 2009 to 2010 to 2019, we saw some significant reductions in intensity forecast error, especially starting out here at about 24 hours out to day 5. We've seen some further reductions in error just in the last couple of years. You can see now that, say, at 72 hours, our average intensity forecast error is below 10 knots, whereas 20 years ago, it was close to 20 knots. So we've cut those errors not quite in half, but we've made some significant progress. And this is largely due to improvements in numerical modeling, models like HWRF that I just talked about, better use of observational data in the models. We're getting Hurricane Hunter, aircraft reconnaissance data, dropsondes, radar, flight level winds, all that's now getting assimilated into some of the models. And that's really helping improve their initial depiction of the structure of the storm, which helps make the intensity forecast better. And then also improvements in forecasting rapid intensification that I'll talk about next. And this has helped bringing those average forecast errors down as well. So what we're looking at here are histograms of intensity forecast errors on the left when rapid intensification was observed or forecast between 2015 and 2017. And here's the 0 line here. So that's where you want to be. But you can see that these are 24-hour errors. The average 24-hour error from the NHC forecast in those cases was about 20 knots too low. And you can see the whole distribution is shifted to the left. There are very few forecasts with any positive errors. Almost all the errors are 20, 10, 20, 30, or even 40, 50. And you have some really big errors out here, 60, 70, 80 knots in 24 hours, where you're totally missing some significant rapid intensification events. Now, if you jump ahead to the last 2 seasons, you can see that error distribution looks a lot different. It's shifted more over to the right. These really large outliers out here are gone in terms of the negative 50, 60, and 70 knot errors. We're starting to see some more positive errors where we're 20, 10, 20, or 25 knots too high. So we're starting to see what looks more like a normal distribution. This looks more like the typical intensity forecast error distribution for all storms. So the rapid intensification errors are starting to trend more towards the typical intensity forecast error distribution. And you can see the average error now in the last couple of seasons in these RI cases in the first 24 hours is now 10 knots too low instead of 20 knots too low. So we're seeing some improvements here. We're not where we need to be in terms of an end state, but this is the first time we've ever really seen this kind of progress. And by getting rid of some of these really large errors, you're starting to bring your average error down as well for all cases. So let's talk now about some of the NHC products. We'll first start with the Tropical Weather Outlook, which is sort of your baseline situational awareness tool that tells you, hey, what's going on in terms of potential, the potential for tropical cyclone development during the next 5 days. Do we have any systems we're monitoring? If we do, what are their chances of development over the next 48 hours and in the next 5 days? And this is issued 4 times a day for the Atlantic and the Eastern North Pacific basins at 0, 6, 12, and 1800 UTC. So we have the text product, but we also have 2 graphics. We have a 2-day formation chance graphic that shows the location of areas of disturbed weather or disturbances that we're talking about in the outlook. And their location is shown with an X that's color coded by their formation chance during the next 48 hours, low, medium, or high. And it also gives you the probability of that system developing in 48 hours or becoming at least a tropical depression to the nearest 10%. We have a 5-day version of the graphic that also shows you the formation potential during the next 5 days. And in addition to showing you where the system is now, if it exists, it also shows you an area where we expect formation could occur. So for this system here in the Central Atlantic, it's located here in this region. We're not expecting it to develop until it starts to turn more eastward and moves into this sort of red hatched area. This system here in the Eastern Atlantic has a low chance of formation in this yellow area over the next 5 days. And then we have another high chance of formation in the western part of the basin. And the color coding or the color shading is determined by the 5-day formation chance. So the 2-day graphic is showing you sort of what's going on now and in the very short term. And the 5-day graphic shows you what can happen over the next 5 days. And these graphical products are issued with every issuance of the text TWO. Other products that start to talk about uncertainty. So we have the cone graphic, which has been around now for more than basically about 20 years. It shows you the probable track of the center of the tropical cyclone, and it's formed by connecting circles that are centered on each forecast point, such that based on our 5-year track forecast error, the actual storm position would fall inside the circle at that forecast time about 2/3 of the time. So again, you can see the circles get bigger as you go out into the forecast period. The size of the cone does not change during a given season, but the cone is only telling you about where the center of the storm might go or might be about 2/3 of the time. It doesn't tell you anything about hazards. So that's a very important thing to remember. There's no information about wind hazards, marine hazards, storm surge, rainfall, storm size, or in the forecast cone itself. We do have a version of the cone graphic that shows the initial size of the tropical storm and hurricane force wind field. That's what's shown here from Irma in 2017. And you can see how much bigger the wind field is than the cone itself, and actually that the coastal watches and warnings are placed well outside the cone, and impacts will occur well outside of the area encircled by the cone itself. And remember, the way the cone is developed statistically, the center should move outside the cone about 1/3 of the time based on our previous 5 years of track forecast error. I want to talk now about the forecast discussion. This is the product that the hurricane specialist writes every 6 hours as part of the forecast package. And it's really the forecaster's chance to talk about what they know, what they don't know, what the uncertainty or confidence in the forecast is, how the forecast is changing. It allows us to talk about the reasoning for the forecast, the reasoning for the analysis of the storm, what's the important observations that we're looking at, how do we think the forecast might change. So you can see here, we're talking in this first paragraph about data from the aircraft, why we're analyzing the initial intensity of Irma at 150 knots, there's some fluctuations in intensity likely due to eye wall replacement cycles. There's been no change in the guidance in the terms of the track in the next paragraph, which brings the core of Irma near Southeast Florida in about 3 days. Then we have the key messages, which are really talking about forecast confidence and highlighting the hazards, especially the land areas, where we're going to talk about the potential for wind, storm surge, rainfall, flooding, tornadoes, rip currents, again, hazards that are typically focused on the land areas. and talk about uncertainty in the forecast. And we could be messaging different stages of the storm in these key messages as well. We're talking about the Hispaniola, the Turks and Caicos, Cuba, Florida, and elsewhere in the southeastern United States. And then at the bottom of the forecast discussion is a table of our track and intensity forecast out through 5 days. We also have the wind speed probabilities. Now this is a very hazard specific product. It's telling you the chances of seeing sustained 34, 50, or 64 knot winds at a particular location. So there is a text product that comes out with every advisory package that has a fixed set of locations, and it tells you the overall chance or the cumulative chance probabilities of seeing those winds during the next 5 days. And there's also information about the onset time. And then we have graphical wind speed probability products that are again showing you for each wind threshold, 34, 50, or 64 knots, the probability of a given location seeing those wind speeds over the next 5 days in association with that particular tropical cyclone. And the wind speed probabilities, as we'll talk a little bit more about, account for the official forecast, but also typical forecast uncertainty in the track and the intensity and the size of the storm. Because we all know, we just talked about what the track and the intensity errors are, and we all know there's uncertainty in the forecasting the size of the storm as well. So to provide a realistic depiction of the risk from the wind hazards, we have to account for that forecast uncertainty. Here's how the wind speed probabilities are created. So we create 1,000 realistic alternate scenarios, or realizations that we call them, that are centered around the official forecast, and they're represented by each of these thin lines. The official forecast is shown by the hurricane symbols. And these are created by sampling the track and intensity forecast errors that the Hurricane Center has made over the last 5 years. And as you watch these realizations move out away from the official forecast, you can see that some of them move to the right, to the left, faster or slower. Those are all realistic track forecast errors that we've made over the last 5 seasons. Some of the realizations are stronger and weaker than our intensity forecast. And then we have a climatology and persistence wind radii model that creates a 34, 50, and 64 knot wind field around each of these 1,000 scenarios. And then we see where those winds move during the forecast period. It does account for weakening over land as these realizations move inland, that you can see they go from being red and orange to yellow and blue, or yellow and green as they weaken realistically, even if the official forecast has the system farther offshore. And there is some measure of how much agreement or disagreement there is amongst the track model guidance that determines how much the spread of the realizations will increase or decrease away from the official forecast. So if we're interested in a particular location, we have these 1,000 scenarios. Say we're interested in New York City. We want to know what's the probability of getting tropical storm force winds in New York City. We count up that out of these 1,000 scenarios, 590 of them produce tropical storm force winds at New York. So that means there's a 59% chance of tropical storm force winds at New York City. And that's the calculation that is done at every point on the maps that we just looked at. Another piece of information that falls out of the wind speed probabilities is timing. And we introduced these time of arrival of 34 knot wind graphics in 2017. They've been very well received. And there are 2 versions of this that provide an earliest reasonable and a most likely time of arrival of tropical storm force winds at a particular location. And again, because it's using the wind speed probabilities, it's accounting for the uncertainty in the track and the intensity and size of the storm. So we have an earliest reasonable arrival time that is based on a very conservative timing. It's the 10th percentile of the distribution, such that there's only a 10% chance that at that location, tropical storm force winds will start earlier than the time indicated on the graphic. So for example, if you're here in Southeast Louisiana, the earliest reasonable arrival time of tropical storm force winds is sometime Tuesday evening. The most likely time of arrival is more the midpoint of the distribution. There's an equal chance that the winds will begin before or after this time. And you can see in this particular case, the most likely time of arrival of the tropical storm force winds in southeastern Louisiana is around 8 a.m. Wednesday. So you can see in this particular case, there's about a 12-hour range of wind arrival times. It's most likely that they'll start Wednesday morning, but they could start as early as Tuesday evening because, say, the storm speeds up, or the wind field gets larger, or the storm moves closer to a given area, or it gets stronger. All of those factors are going to go into the wind timing. And that's certainly a critical threshold for a lot of users, marine customers, customers on land, emergency managers. Everybody's very interested in the arrival time of those sustained tropical storm force winds. On the storm surge side, we have a potential storm surge flooding map or inundation graphic that is, again, a risk map that shows you and shows users the height above ground that water could reach from storm surge at a given location. It's basically a reasonable worst case scenario that only has a 10% chance of being exceeded at a given particular point. And the first potential storm surge flooding map is usually issued when we first put out a storm surge watch for the United States. And it's available about an hour to an hour and a half after the advisory comes out. So there's a bit of a lag here because we have to do a lot of runs, hundreds of runs of a storm surge model to, again, account for the uncertainty in the track, intensity, structure, forward speed of the storm. And that risk map falls out of those calculations. Again, it's helping folks plan for a reasonable worst case scenario. So let's talk about watches and warnings. So these are coastal watches and warnings that are going to be included in NHC's hurricane product suite, are really coastal watches and warnings for land areas or islands. But the definitions are somewhat analogous to the marine tropical storm watches and warnings that are going to be in high seas and offshore waters forecast. For a tropical storm watch, that generally means that tropical storm conditions are possible somewhere within the watch area within about 48 hours. A tropical storm warning means that tropical storm conditions are expected somewhere within the warning area within 36 hours. And when we lay out these watch warning areas, we have to account for the uncertainty in the track, intensity, and size of the storm. So the warnings are not a forecast. It's not telling you that tropical storm force winds are going to occur at a particular location. It's telling you that everywhere in that warning area, everybody needs to prepare as if those tropical storm force winds could occur or are going to occur somewhere in that area. It's just that, say, at 36 hours out, our average track forecast error is 50 nautical miles. And depending on the angle of approach of the storm to the coastline, we have to pay attention. We have to account for that uncertainty, also the uncertainty in the size and the intensity of the storm when we lay out the watches and warnings. For hurricane watch and warning, similar definitions. Hurricane conditions are possible within the watch area within 48 hours. Hurricane warning means conditions are expected somewhere within the warning area, not everywhere, but somewhere within 36 hours. And the lead time for the hurricane watches and warnings is tied to the arrival time of tropical storm force winds along the coastline. On the storm surge front, similar paradigm here. We introduced a storm surge watch and warning for the United States in 2017. We've used it numerous times over the past several years. And the storm surge watch and warning was really devised to help enhance the public response largely for evacuation decisions that are made by local officials, and really highlight the areas that are at risk of life-threatening inundation from storm surge, because that doesn't always match up with the area that's at risk of, say, hurricane force winds. The watch and warning are issued, again, 48 to 36 hours before the arrival of life-threatening surge or some other hazard that would hinder evacuation. So it could be issued with the lead time to the arrival of the tropical storm force winds or when we think the water is going to rise. And the storm surge watch and warning are collaborated between the hurricane specialists here at NHC, the storm surge unit, and local forecast offices. I talked about watch warning considerations and how we have to account for the uncertainty in the forecast track, the size of the storm, how we think the forecast might change, and that's going to determine the size of the area that we put up a watch or warning for. So this is an example of a storm approaching the southeastern coast of the US. If the hurricane force winds are occurring within this yellow circle, well, here's our 36-hour forecast. We're not going to just put out a hurricane warning for this yellow circle area, knowing that the average track forecast area at 36 hours is 50 miles. So the storm could be over here, it could be over here. So everywhere within that warning area along the coast of Georgia up to southern North Carolina is at risk of hurricane force winds. Other considerations for watches and warnings include continuity. We want to maintain continuity when we can with previous watch warning decisions. We're not issuing watches and warnings for severe thunderstorms. We're issuing them for hurricanes, which are sort of long fused synoptic scale events that could last hours to days. We have to understand what the potential future changes are to the NHC forecast. If we're forecasting a storm and we're expecting it to continue to get stronger, or we expect our intensity forecast to continue going up, or we expect the track forecast to continue to be adjusted in a certain direction, we will account for that when we put up watches and warnings. The Forecasters making an assessment of their assessment of the uncertainty in the track and the intensity and size of the forecast. What's the vulnerability of the area being affected? And what's the time of day or day of the week? Do we want to issue a hurricane warning at 11 p.m. on a Friday night? Probably not. We probably would try to issue it earlier, even if it's a little ahead of the particular lead time. On the international side, we are the World Meteorological Organization Regional Specialized Meteorological Center for the Atlantic and the Eastern North Pacific. And based on our forecast and our reasoning, we will recommend the placement of watches and warnings to other countries, but they are ultimately responsible for issuing watches and warnings for their respective areas. We do a lot of coordination with other countries. This is just a particular map that shows all the different countries in the Caribbean, especially in the Lesser Antilles. Make a lot of phone calls to the various islands, want to make sure we get that information correct in our products. And we want to make sure that the islands are trying to coordinate amongst each other and make sure that they have a coherent depiction of risk through the area. I want to talk briefly about potential tropical cyclones. This is a concept we introduced in 2017 that allows us to basically start issuing forecasts and watches and warnings for systems that aren't yet tropical depressions or tropical storms, but could bring at least tropical storm conditions to land within 48 hours. And it basically allows us to go ahead and issue watches and warnings in our full advisory package at that time. And it provides longer lead time forecasts for areas downstream, like you see in this case, where we're issuing the potential tropical cyclone advisories to cover the threat here to the Leeward Islands, Puerto Rico, portions of Hispaniola. But now we have a 3, 4, and 5 day forecast taking a storm through the Bahamas and near Cuba and Florida. So the one caveat to point out is that there's larger than usual uncertainty with these forecasts, especially on the track end in the first 2 to 3 days, because we're typically dealing with a system that's relatively weak and disorganized. We might not have a well-defined center or something that's easy to track. So the forecast can jump around a bit. So we try to have to cast a relatively wide net with things like watches and warnings and information about the hazards and not get too focused on the details of the forecast. So quickly, some changes for 2022. You probably have already seen this if you've been looking at the tropical weather outlook, although the Atlantic TWO hasn't had much in it for a couple of weeks. We are introducing sort of geographic headers for the systems that are in the outlook, so that if you're looking at the text product itself, especially just the text product, it helps you figure out which system we're talking about if we have 3 or 4 systems in there. It improves the readability of the product, and it helps minimize confusion when we have multiple systems in the text. We have the experimental peak storm surge forecast graphic again this year. We made some changes to it with adding some color, some more easily readable text. This graphic is basically showing the forecast peak storm surge inundation expected to occur somewhere within the outlined area along the coast. This is a graphical depiction of the storm surge information that's in the NHC public advisory, and we typically introduce it when there's a storm surge watch or warning in effect. Looking ahead, where are we headed? Well, we're experimenting with day 6 and 7 track and intensity forecast. The average track forecast error at day 7 is not too bad, but we have about 7% of those forecasts have errors that are really, really big, greater than 500 nautical miles. So we're trying to figure out how we're going to depict those longer range track forecasts and how we want to best depict that uncertainty. Here's an example from Hurricane Florence back in 2018. We had a 7-day forecast we made for Florence that showed recurvature well east of Bermuda and had an error of about 675 nautical miles. So if this was a forecast that had been public, how might have it affected decisions that have been made by mariners or other users up here in the North Atlantic or off the US East Coast, showing a storm that was going to probably recurve well east of Bermuda, but then instead moved much farther west and ended up making landfall in North Carolina. So how do we depict that information in a way that's useful to users? And we need to make sure we have probabilistic products that extend out to that day 6 and 7 time frame going forward. We don't have a lot of intensity guidance beyond day 5 at this point either, so we need to develop that. We want to make sure we have things like wind speed probabilities at longer time ranges. So we're interested in hearing from the marine community, what sort of uncertainty information is useful for you given the average track and intensity errors at day 6 and 7. And like we said, we have some social science work that is going on that will hopefully help us figure out how to disseminate this forecast information in a useful way for users, because we know that there is a demand for forecast information at longer lead times, and we think we can provide some of that, but we want to make sure we do so in a way that's useful. We are looking at also making 7-day Genesis forecasts. This is a reliability diagram showing our 2-day, 5-day, and 7-day Genesis probabilities in the Atlantic Basin over the last 3 years. And you can see that the 7-day Genesis probabilities are pretty reliable. And sometimes they're more reliable than the 2 and the 5-day. They have a little bit of a low bias from 10 to 40% and around 70 to 90%. But overall, as our Genesis forecast probabilities increase, the actual incidence of Genesis increases as well. So these are pretty good forecasts. You can see this is a big sample of over 2,300. Similar pattern in the Eastern Pacific. Our Genesis forecasts are pretty well calibrated across the probability spectrum. So we may try to do something experimental or some sort of public depiction of 7-day Genesis forecasts as soon as next year in the tropical weather outlook. So stay tuned for that. And that's all I've got. I'll be glad to take any questions or comments you have now, or you can certainly drop me an email and I'll be glad to help you out. So thanks very much for the opportunity to talk with you all today.
Thanks, Mike. Right now, we only have one question, and that is from Sean McMillan. What are the NHC expectations for improved forecasting given the new supercomputers coming online in the near future, and where will they improve upon existing forecasting?
Yeah, that's a good question. The new supercomputers that NOAA we just transitioned to them, I think, last month. So the big feat there was to just move everything onto them. And then now we can start working on the development of new models and new implementations for that can run on the new supercomputer. I think one of the big things we're looking for is there's a new hurricane forecasting model called HAFS that is running experimentally now and is slated to replace the HWRF model and have some different versions of that I think will help, hopefully improve intensity forecasting. I think we're looking forward to more ensembles that run at higher resolution and more members that will help improve track and intensity and size forecasting going forward. We're also hopeful that we'll be able to run more sophisticated, higher resolution wind speed probabilities on the new supercomputer and improve the storm surge modeling capacity as well. So I think that's sort of where we're headed. We don't develop, most of the models we don't develop ourselves, but we're involved in the evaluation and decision making about implementing them with our partners at the Environmental Modeling Center, part of the Weather Service.
Thanks, Mike. And we got another question. I don't know if Chris is able to chime in on this. David Jones asks, how can these forecasts be accessed from a boat on the ocean that is not able to listen to local forecasts?
Yeah, I could address that. It really depends on the technology you have available. Within about 20 or 30 miles of the coast, NOAA weather radio works well. If you're further offshore, if you have any internet access, that would be the best way to get a hold of our graphics and grids, as well as the Hurricane Specialist Unit's information. If you have satellite communications through the Global Marine Distress and Safety System, that's a way that you can get the high seas forecast that we issue and the Ocean Prediction Center issues, as well as the TCM text product that the Hurricane Specialist Unit issues. There's also FTP mail, where one can ask for a specific marine product by email. There's also the radio fax. So if you have a high frequency radio receiver, you can get that. And then finally, there's VOBRA, the voice broadcast, similar to NOAA weather radio, but at a higher frequency. So it really depends on the technology you have aboard on your ship and where you're at. I'm going to go in detail about these different opportunities tomorrow during the Marine Talk.
Right, thanks, Chris. And back to Mike. Michael Doherty asks, is AI being included in forecasting models?
Yeah, there are some early efforts at developing artificial intelligence and things like neural networks into especially intensity forecasting. So I think there have been some early results there, but it's not anything that as far as I'm aware of, is running in anything that's being done operationally. I think it's still sort of more in the active research phase. But I think,
and sorry, Mike.
I think it's these types of very complicated multi-scale problems like intensity forecasting probably lend themselves to AI type approaches, going forward. I think that's a fruitful area for potentially making improvements.
All right, and Sam Milton has asked, with Bonnie, there's a long period where the storm didn't have a well-defined center or closed wind field, which delayed it being called a tropical cyclone. Does that negatively affect preparedness?
Well, I don't necessarily think so, because the impacts were probably about the same. We carried Bonnie as a potential tropical cyclone, I think, for 3 days or more. But if we hadn't had that, we had that option, for example, we would have been waiting for a system to form and not being able to really provide any forecast information for a system like that. And we certainly would have been had less lead time for what ended up being a pretty strong tropical storm that made landfall in Central America. So I think just having a forecast from the Hurricane Center out there can be sort of a centralizing, unifying tool for messaging for a system, even if it hasn't quite crossed the line to be a tropical depression or tropical storm. So I think I think the service enhancement outweighs any potential confusion or lack of understanding about why something isn't quite yet a tropical cyclone. Because before, we would have either had to just wait, or we would have had to sort of fake it and call it a tropical storm when it wasn't one yet. So to get this from the service perspective. So this lets us cover the service aspect and still be true to the science aspect of calling things what we think they are.
All right, and Daniel Cruz has asked, can you tell us more about the model coming in to replace the HWRF?
Yeah, HAFS, the Hurricane Analysis and Forecast System. So there's actually multiple flavors of HAFS that are being experimented with and run, that are being developed by EMC and the Hurricane Research Division, where there are versions that run in sort of a single storm nest mode like the HWRF runs now, one storm at a time. There are also versions of HAFS that run on a basin scale that cover, say, the entire Atlantic basin and have embedded nests in there that let the storms interact with each other. And that's something we've never really had on the regional hurricane modeling front before. We have the global models, but they're not really run at a resolution that really resolves fully the hurricane itself. But this sort of basin scale approach to something like HAFS will allow better storm-storm interaction and hopefully result in some improved forecast for track and intensity when we have multiple storms ongoing in the basins. Because interestingly enough, you can have some pretty far afield effects from a storm, say even in the East Pacific, affecting how a storm evolves in the Atlantic, because it's affecting the upper level wind pattern, things like vertical wind shear. And so you can't really look at a tropical cyclone sort of in its own isolated environment. You have to understand how it's interacting with other features in the atmosphere. And I think that's one step in the right direction. I think HAVS has already, in some of the experimental runs, has shown some ability to already improve over HWRF in terms of intensity forecasting. So I think we're excited to see how that evolves over the next year or two.
All right, we have 3 more questions, so hopefully we can get to them. And if anybody else asks questions after that, we'll be sure to email you the answers. Sean McMillan asks, what are your theories, opinions on the recent phenomenon of increased hurricane intensity 24 to 36 hours prior to landfall?
Yeah, we've seen a lot of RI before landfall, especially in the northern Gulf Coast. I don't know if there's any specific trend there. It's just that the conditions have been favorable for it. Some of it's been really well forecast and well anticipated, like Ida last year. Others were not well anticipated, like Michael in 2018, where we saw a storm intensify in what we thought was a moderate shear environment that didn't look very favorable for it. I don't think we have enough to really tell us, if there's any long-term trend in that regard. It's just that, the conditions that come together for rapid intensification usually only align in a very limited area for a limited amount of time, and we've just gotten unlucky with how that's evolved near the Gulf, and other systems rapidly intensifying near land, like Dorian in the Bahamas, or Maria as it approached the northern Leeward Islands. So we've gotten better at anticipating that, and but it's certainly a thing that it's a phenomenon that users need to be aware of, not just the RI, but the storms developing and making landfall within 2 or 3 days, like a Laura or Ida or Michael, where you almost end up with sort of a short fuse hurricane emergency, where you don't have a long track system, but you have something that develops and makes landfall very quickly. So those are some things that we're focused on in terms of messaging and awareness, to just make people aware of the fact that, hey, you can have these systems develop very close to land, and in some cases they're going to intensify and can be some of the strongest storms that end up hitting the United States, for example. Most of them have been storms that developed and were young storms and rapidly intensified up into landfall. Some of those storms happened 100 years ago, so it's not a new phenomenon, but it is something that's happened a few times in the last few years.
All right, Bradford Bengio asks, how are the number of hurricanes distributed over the entire season? Are they spread evenly over the entire time frame of the season? And if the first half of the season is below expectations, does that change the statistics for the second half of the season?
Yeah, you know, most of the hurricane activity and what we call the accumulated cyclone energy, which measures the combined duration and intensity of storms, really is concentrated in the August, September, October timeframe, really those peak 3 months of the season. You know, so what happens early in the season, like June and July, doesn't usually have a whole lot to do with what happens in the peak of the season, because the peak of the season is really driven by storms that come out of the deep tropics and the main development region that originate from tropical waves out in the eastern Atlantic or develop in the Atlantic and move into the Caribbean and Gulf of Mexico and into the Gulf or the southwestern Atlantic. So storms that tend to form really early in the season in June tend to form from other pathways. They tend to form off fronts or near the you know, sort of more non-tropical origins. So, you know, the seasonal forecast skill, as I understand it, and Chris can chime in on this if he wants, but is mostly focused on those sort of peak season, main development region type storms. We're not, the seasonal forecast is not as good at anticipating storms that form in the subtropics or mid latitudes, and those typically aren't the most impactful long-lived storms as well. So typically peak of the season, typically most of that comes out of the deep tropics where most of the major hurricanes form.
All right, this question is a little subjective, but Hoop Vandermark asks, is there normally in the Caribbean enough time while at sea to sail away for a hurricane at 4 knots speed if you have information about the hurricane on board through internet?
That's a great question. Probably depends on how fast the hurricane's moving and how good the forecast is, and you know, but that's something that would probably be pretty case dependent and pretty vessel dependent and situationally dependent. So I'm not sure.
And then we just have one more really fast, we can get into it. Do we have tools to monitor the loop current eddies in the Gulf and their effects on SST and RI?
Yeah, we do. We have satellite, hold on, my computer locked up on me for some reason. So hopefully you can still hear me. Yeah, we do. We have, you know, satellite altimetry that basically can measure the depth of warm water and can give us a picture of the 3-dimensional upper ocean structure, so we can see how things like the loop current evolve. And those real-time analyses of ocean conditions do go into models like HWRF, so they have an accurate depiction of what the upper ocean looks like, and that can help us predict intensity. And some of the statistical models that we use for intensity forecasting also account for upper ocean heat content as well. So that's something that can be taken into account. You got to get the track forecast right, though. You got to get it to move, you know, if it's going to move over that warm ocean eddy, sometimes that's hard to determine 3 or 4 days out if your track forecast area is 150 miles. So, but if you can get the track forecast right, we generally have enough knowledge of what the upper ocean conditions look like that we should be able to take that into account. But that's not the whole story. We have to understand what's going on in the atmosphere in terms of shear or dry air or any other favorable or unfavorable characteristics that might affect intensity change.
All right, that's all the questions we have. Thank you very much, Mike, for sticking around and answering all those questions. And thanks everybody for attending today.
Thanks, everybody.
All right, see everybody back here tomorrow at 3 p.m. for Chris's presentation on Task B products and services.